Welcome to Lecture 1, Part 2 for Chemistry 418, Radiochemistry. This is the second part of the introduction lecture. The first lecture covered class organization and the history of radiation research. We ended with the discovery of the actinide elements. Part 2 is going to talk about the chart of the nuclides and table of the isotopes. We're going to go over the description and use of these databases and how the data is presented. And then we'll talk about atomic properties, nuclear nomenclature, X-rays, so we identify the difference between X-rays and gamma rays, the types of decays, and then forces, the four basic forces of nature. And this will be the limit of the course instruction. We'll go up to the forces of nature. So we should start by discussing the definition of radiochemistry. There's a few different definitions people use. One could be the chemistry of radioactive isotopes and elements, utilization of nuclear properties in evaluating and understanding chemistry, and one that I like is the intersection of the chart of the nuclides and the periodic table. I prefer this one because it shows that the chart of the nuclides are nuclear properties, periodic table of chemical properties, and as a radiochemist you transition back and forth between nuclear properties and chemical properties. So some of the things that we should understand when we talk about radiochemistry, let's start, since we want to talk about the nucleus and nuclear properties, let's start with that. The nucleus we can always describe as the number of Z protons and N number of neutrons in a nucleus. The diameter of the nucleus is about 10 to the minus 14 meters. And electron interactions with the nucleus, that's going to be the basis of chemical properties. Electrons are, those orbitals are on the order of 10 to the minus 10 meters. So the bulk of the radius and volume of an atom is composed of electrons, but the bulk of the mass, the small area, is occupied in the nucleus. And electrons, they can be excited, they can get into higher energy orbitals, they can undergo ionization. These binding energies of electrons can affect ionization. That changes some of the chemical properties, so different oxidation states. This will come into play more when we talk about the actinides, where there's multiple oxidation states. And that has to do with the fact that electrons are being loaded up into those electron orbitals, and the energy differences between the different orbitals are very small. So some of the terms that we have for atoms within radiochemistry, we've already discussed. Isotopes. So an isotope is the same Z, so the same proton number and different neutron numbers. An isobar, where we have the same A, the sum of the protons and neutrons. So as an isotope undergoes beta decay, it converts a neutron into a proton. So the sum, the A, remains the same. An isotone, that's the same number of neutrons but different number of protons. This is used to help identify how the neutrons and the protons have properties within the nucleus. And then something we've already mentioned, the isomer. So technetium-99m, that little M state. And it's a nucleus in an excited nuclear state. And the one way that we can describe a certain isotope is to have, as shown here, a chemical symbol with A, Z, the proton number, and possibly the neutron number listed here. The types of decays that we'll discuss within the course are listed here. Alpha decay, which we've already discussed, occurs among the heaviest elements. An example here is radium-226 that decays by an alpha that makes radon-220 and then energy. So energy is a common component of every alpha decay, and of every particle decay. This energy is actually the conversion of mass into energy. So E equals mc squared. Beta minus, in this case, a neutron is converted into a proton, so it moves up the periodic table. a beta particle, which is an electron, an antineutrino, and energy are produced. Positron decay, so these are in neutron deficient nuclides, where a proton is converted into a neutron, so it moves down the periodic table. A positron, which is the anti-particle of an electron, so it's the antimatter particle of an electron, and a neutrino are produced along with energy. Electron capture, where an isotope will capture one of its orbital electrons, it will use that, it will convert a proton into a neutron, so move down the periodic table, gives off a neutrino and energy. And then a final type of decay is spontaneous fission, where an isotope will spontaneously break into two components. An example here is californium-252 going to an isotope of xenon, an isotope of ruthenium, and then some neutrons, and of course with energy produced. These aren't the only decays. There are other more exotic decays that we'll discuss in the course, but these are the primary decays that are dominant in the chart of the nuclides. From the last decay we discussed, fission, one thing that's produced are the fission products. And the fission products, as we showed earlier, there's xenon, ruthenium, but you can get a probabilistic distribution of fission products as shown here for, in the green, uranium-233, in the red for uranium-235, and in the blue here for plutonium-239. See that there's a light peak and a heavy peak. There's these two variations that are shown. We're going to learn that the fission product distribution is dominated by the production of an isotope with a mass of 132, because that has two interesting nuclear properties associated with it. And we see here that this heavy fragment is pretty consistent regardless of what isotope undergoes fission, but the light fragment changes. So the uranium-233 is lighter, the uranium-235 is a little bit more, and the plutonium-239 is a little bit more, a little bit heavier. We can also see the influence of neutron energy. Now again, this is admittedly a log scale, but as we see, as the neutron energy increases, this valley area on the fission product distribution curve decreases. So there are two things going on that can change information about fission. One is the material that's undergoing the fission. We see a fission product distribution change. And then two is the energy of the neutron can also have an influence on the fission product distribution change. And here to note, if you wanted to identify which was the fuel, which fuel produced these isotopes, imagine if you looked at a ratio of zirconium to technetium, uranium-233, high amount of zirconium, low amount of technetium. The red uranium-235, about equal amounts zirconium, technetium, and plutonium-239, low amount of zirconium, high amount of technetium. Photon emission is observed through two routes in radiochemistry. One is through gamma decay, where an excited nuclear state de-excites by emission of a photon. So this can occur when a radioactive isotope decays to a daughter. It may not decay to the ground state directly. It may decay to an excited nuclear state. That nuclear state often has a lifetime on the order of nanoseconds to picoseconds. However, something that is metastable has a much longer lifetime, can be hours, can even be years. For instance, technetium-99m is on the order of 6 hours. And it will stay in this excited state, decay by emission of a photon. Now, X-rays are also photon emission, but that's from the electron level. So it's not from the nucleus itself. And I'm sure you've seen this in previous courses. But a lower energy, a lower orbital electron is removed. Electrons from the higher higher occupancy occupy that space, and a photon is emitted with that change. You can also get X-rays from deacceleration of high energy electrons, and you can also get electron transitions from the inner orbitals. So you get a number of these changes occurring, producing these X-rays. One can produce X-rays by bombarding of metal with high-energy electrons. You can have synchrotron light sources. You can have radioactive sources. So you can have a number of different sources that are used to produce these X-rays. And as shown here, one can remove, for example, a K orbital. The electrons that go down to fill those K orbitals they can be defined by the transitions. Those transition, the energy, which is shown here, the square root of the frequencies as a function of atomic number, are shown to have a relationship. You can actually identify that relationship here. And what this means is that the X-rays can be used to identify the elements that are emitting those X-rays. So X-ray fluorescence is a powerful tool to identify elements from materials. And again, as we discussed earlier, Moseley in 1913 showed this relationship. The chart of the nuclides provides a bulk of the information we're going to use in the course on the isotopes. Initially, information on the chemical elements are given. For instance, as shown here, you can get the atomic mass, the average cross-section for each element. There's also nuclide information. So for any given isotope, you can see the spin and parity. So for instance, shown here, boron 8 is 2 plus, carbon 12, it's blank, that's because it's 0 plus. Spin and parity 0 plus for even nuclides, so they don't even list those. Carbon 13 is 1/-, so that's 1/2 minus carbon 13 NMR. You can get information on fission yield, we'll show that. You can also get information for stable isotopes, for instance, isotopic abundance, reaction cross-sections, and mass. All the gray elements, all the gray isotopes here are stable. So the data that's provided here is the relative isotopic abundance. So as you see, lithium-6 is 7.59% of the lithium is lithium-6, where the remainder is lithium-7. For radioactive isotopes, data that is provided includes half-life, the modes of the decay and their energies, the beta disintegration energies, the isomeric states. There's information on natural decay series and reaction cross-sections. A key utilization of the chart of the nuclides is understanding isotope decay. From the legend on the chart of the nuclides, you'll see this little figure where it says the origin nucleus, and anything that comes with the word out, that has to do with a decay. In means that if I hit this nucleus with an alpha particle, this would form. If I hit it with a proton, this isotope would form. Now, if we look at decay, if I emit an alpha particle, it goes from the original down diagonally 2. If a beta minus comes out, it moves up diagonally 1. And if a positron, or it decays by positron emission or by electron capture, it goes down diagonally. So let's take a look at an example of the area of the chart of the nuclides. If we look at something like plutonium-235, this symbol here is electron capture. So plutonium-235 decays, if I follow here, goes this way, and it decays to neptunium-235. It's going down because it's taking an excess proton and converting it to a neutron. If I have something such as protactinium-235, it decays by this beta minus, which is here, and it takes an extra neutron and converts it to a proton, so it moves up to uranium-235. And then if I have something like plutonium-238, it decays by alpha. There's a little alpha here. The original nucleus alpha out, so it goes down 2. And this plutonium-238 kicks out an alpha and makes uranium-234. So it's a loss of 2 protons and 2 neutrons, so it goes down by 2 protons and over by 2 neutrons. So it's a total mass loss of 4, but going down 2 rows. And you can use the chart of the nuclides to understand all sorts of decays and nuclear reactions. For instance, one is the formation of this isotope, plutonium-238, which will describe its uses. It's used in space exploration as a heat source to produce electricity in spacecraft. And we'll discuss this and other isotopes during the course. The legend of the chart of the nuclides is useful for demonstrating the information that's provided in the database. The chemical elements given, so for instance as shown here for lithium, the atomic mass on the carbon-12 scale, there was a time when oxygen-16 was used as the scale, the name of the element, and then the thermal neutron absorption cross-section in Barnes for the element, followed by the integral cross-section, also in Barnes. For a stable isotope, which is listed in gray, stable or very long-lived isotopes are in gray, you get the symbol, the mass, the atomic percent abundance, the ground states of even Z, the ground state spin in parity, as we stated earlier, even nuclei are 0+. The thermal cross-section in Barnes leading to isomeric and ground state, and the resonance cross-section in Barnes, isomeric and ground state. This triangle here means that this isotope is produced from the fission, and this is the mass of the isotope. We will describe cross-section in more detail when we discuss nuclear. Moving on to the radioactive isotopes. Their mass and symbol shown here. It's non-gray. The color has to do with the half-life of the isotope, which can be seen in the legend. Spin in parity, again 5/ minus is 5/2 minus. The half-life 10.98 days. The modes of decay followed by their energy with MeV for alpha and beta, KeV for gammas. So this decays with an energy of 0.805 MeV beta. So beta is listed here. The gamma is 91.1 KeV. The cross-section information and the beta disintegration energy. As you see, the beta disintegration energy is a little bit higher than the beta decay energy, so some of the energy is going elsewhere, possibly to a gamma decay. And then again, this triangle says that it is a fission product from the slow neutron fission of uranium-235. Okay, here are some naturally occurring radioactive isotopes. The gray, again, it's stable, but these are long-lived, so it's long-lived or stable. This black bar, this is the indicator that it's naturally occurring. So lanthanum-138, a spin of 5+. This is the abundance, so 0.09% of lanthanum is this isotope. The half-life is 1 × 10⁻11 years. So 1 × 10⁻11 years, if Earth is 4.5 billion years old, the half-life is longer than the age of the planet. Again, modes of decay, E, this E here is electron capture, beta minus, gamma, cross-section information, and isotopic mass. And this square, as opposed to the triangle, means that it's a shielded fission product. It's still a fission product, but we'll discuss what shielded means. It means that there's a stable isotope in front of it, so it doesn't get fed along the 138 decay chain. Other information is shown here. This is a historic symbol. So lead-210 was also known as radium-D. It was the 4th daughter down from the decay of radium. So historically, you've got this name radium-D. That'll be shown. You'll see some boxes that are split. So this is a metastable state, ground state, so metastable state, spin in parity, half-life, decay modes, ground state, spin in parity, This is stable, so this is the atomic abundance. And then two isomeric states that are both radioactive, so tellurium-131. The metastable state, spin and parity, 11 halves minus. Ground state, 3 halves plus. The half-life of each state, and then the other data as we discussed.
The chart of the nuclides also utilizes symbols and colors to convey information. Radiation and decay symbols are shown here. The common ones we'll discuss in the course include alpha decay, beta minus, beta plus, gamma decay, and electron capture. Other decay routes also occur. Some of the more exotic ones that we'll introduce in the course include neutron emission, proton emission, double beta decay, and cluster decay. Time is also shown as symbols. One that is different that should be pointed out is years, which is symbolized by A in the chart of the nuclides. Colors are also used to convey half-life times and cross-sections. Examples are shown here where the orange color for time covers half-lives on the order of 1 day to 10 days, yellow for 10 to 100, and then all the way up to gray with half-lives from 5 times 10 to the 8th years to stable isotopes. Similar use of colors shows the differences in cross-sections, as shown here from 10 barns to 1,000 barns. Example of isotopes showing these differences in colors are shown here. For example, rhenium-187, although radioactive, has a half-life that is greater than 5 times 10 to the 8th years and can be considered stable. Other shorter-lived isotopes are shown here, such as iridium-192, which has a half-life of 73 days, and it's yellow. And then for cross-sections, a cross-section of something between 10 and 100 barns is shown for osmium-193. Other symbols include the sigma for a cross-section, B for a barn, and then these Greek symbols for a weak abundance, a very weak abundance, or a very, very weak abundance, which is symbolized by omega and nu. For an example, in the metastable state of iridium-192, the isomeric transition at 155.2 keV is shown with an omega following it, which means it's a weak abundance. So under 1% of the time it occurs.
We also stated that the fission yields for a given isobar can be identified in the chart of the nuclides. Here's an example. It says fission yields of uranium-233 and plutonium-239. The 239 is in parentheses. So for a given isobar, for instance, this 102, this 2.4 is for the fission yield of uranium-233. Plutonium-239 is in parentheses. So 1.6% of the time it produces, when plutonium fissions, it produces a fission product with a mass of 102. Uranium-233, when it fissions through thermal neutrons, 2.4% of the time it produces a fission product with a mass of 102. And I do want you to note that if you look at the plutonium values, they go from 5.4, they peak at around 7, and they start going back down to 2.2%. So something that's close to 7%, 6% is a very high fission yield. There's similar data for fissions from uranium-235. You see it's just on this side. And again, these numbers, they go from 0.03%. They can go even lower. And they shoot up all the way up to about 6.2%, going from an A of 125 to 140. An example of some questions and terms you should be able to identify from what we've covered related to the chart of the nuclides. You should be able to identify isomers, isobars, isotones, and isotopes. So for instance, cobalt-60M is isomeric state. Isotopes, well, cobalt-60M, cobalt-57, cobalt-58. Those are examples of isotopes. Isobars, anything with 57, so cobalt-57, nickel-57, iron-57. You should be able to identify the daughter from the decay of the following isotopes. So for instance, polonium-210, you should be able to go to the chart of the nuclides, see that that decays by alpha, that goes to lead-206. You should be able to identify, look at these other isotopes, identify those. For instance, bismuth-212 has both alpha and beta, so it decays by alpha and beta, certain percentages. And then you should be able to identify that lead-208 would not decay. It's in fact stable because it's gray. You should be able to get an idea of how some isotopes are produced. For instance, carbon-14, naturally occurring radioactive carbon, half-life around 5,000 years. It's on reactions with atmospheric nitrogen. So if you looked at nitrogen-14, you could figure out what reactions are necessary to remove a proton from nitrogen-14 to make carbon-14. And you should be able to, for instance, if a question was asked, identify 5 naturally occurring radioactive radionuclides that are less than a Z of 84, so under polonium. And those are those with the gray boxes with the black bars. Okay, should be able to identify questions like how many stable isotopes of nickel are there. Go to nickel, count the number of gray boxes. What's the mass and isotopic abundance of a given isotope? For instance, strontium-84. The spin and parity of an isotope. The decay modes, so we talked with bismuth-212. What are the isotopes of a given series? The front part of the chart of the nuclides has information on the decay series. What are the half-lives of given isotopes? Lutetium-176, ytterbium-176. How is plutonium-238 produced? How do you make plutonium-239 from uranium-238? We've actually discussed these in the previous lecture, but you should be able to look at the chart of the nuclides and figure that out. Which actinide isotopes are likely to undergo neutron-induced fission? Those with large fission cross sections. So when they capture a neutron, they undergo fission. It's the sigma F. As an example, you can look at the data for uranium-235 or plutonium-239. And which isotopes are likely to undergo alpha decay? The heavier isotopes. So as an example, what is the half-life of tellurium-130? If I look at this, if I look at the, let's see, it's gray. That usually means it's stable, but it's actually extremely long-lived. It's 6 times 10 to the 20th years. And what's the cross-section, what cross-section data is provided for tellurium-130? Well, I've got this thermal and resonance making both the metastable and ground state, metastable and ground state. So I have 4 different reaction cross-sections to consider, because if a neutron, depending upon the energy, if it hits tellurium-130, the neutron energy for thermal neutrons are described here. It can make this metastable or this ground state, and more energetic neutron can make this metastable or this ground state. The table of the isotopes is another a compendium of data that's used in the course, and it contains much more detailed information on each isotope. There's mass decay schemes, mass excesses, particle separations energy, population reactions, gamma transition energies and their intensities, decay levels, and a drawing of the structure. Right now, this is just an introduction to this information. Later in the course, we'll go over this information in much more detail. One can utilize the table of the isotopes in the PDF form as shown here. Opening it up, you would see this page. You can click on the summary scheme index. You would get a table that's shown here. This would allow you to pick any summary of isotopes with a given mass. The mass parabola, for instance, we'll select A of 60. We would click on that. It would pull up information. It would go to this mass parabola as shown here. So these are the isotopes with an A of 60, some fundamental information. For instance, we'd want to look at cobalt 60. We can get more detailed information on cobalt 60 by clicking this. It would bring us to this page, which would give us information on the mass excess, the neutron separation energy, the proton separation energy, the Q value. These are all these terms that we'll define later. Reactions on how they're produced, then branching levels. If I clicked on this value here, it would bring me to here. And this is my decay scheme. And this shows how cobalt 60 with a 5.2714 year half-life, a spin and parity of 5/2 plus, decays to nickel. And as we see that 99.925% of the time it decays to this excited state of nickel. And then that excited state, 99.9% decays to this state, and then 99.98% of the time it decays down to the ground state. So what this would show for cobalt 60, we would get two photons from the gamma decay, one at 1173 keV, and another one is 1332 keV. So the gammas are related to the decay of the cobalt. Each one of these states have a half-life on the order of picoseconds, and they decay rapidly to this stable nickel 60. We'll go over this information in more detail throughout the course. Right now it's just kind of introduction for the data that's available in the table of the isotopes. Another term that we've described is the half-life. And the half-life is the amount of time it takes for half of a radioactive material to disappear. So for instance, if one has some iodine 131 and you measured that it was 25 milligrams, how long would it take it to go from 25 to 12.5 milligrams, to 6.2 milligrams, to 3.1 milligrams? Each one of these is cutting down by a half. It's first order decay. There's actually a fundamental relationship that's shown here where the number of, in this case, atoms, but if I know the number of atoms, I know the mass at a given time is equal to the amount initial times e to the minus lambda t. Lambda, the decay constant, is just equal to log 2, the natural log of 2, divided by the half-life. Now, if this time is in seconds, your half-life needs to be in seconds. If this time is in minutes, your half-life needs to be in minutes. In this first-order decay, this half-life term is fundamental in radioactive decay. Again, this is an equation that we will see frequently in the course. And you can use some of the information we just discussed. For instance, calculate a decay constant. If I give you an isotope and you have the listed half-lives, I can calculate the decay constant in inverse time units. So if it's listed in days here, it would be inverse days. But usually we want the decay constant all in the same time unit. We tend to have seconds. So I can go here. If I have a half-life in days, I need to convert those days to seconds. If I have years, I need to convert those years to seconds. But as we see, the longer the half-life, the smaller the decay constant, because it's log 2 divided by the half-life. So as an example, the selenium-75, the half-life is 119.78 days. Log 2 divided by 119.78 days is equal to 5.79 times 10 to the minus 3 days. But if I want that in seconds, convert the days to hours, hours to seconds, and then I get the decay constant in seconds. Based upon some of the equations that we've reviewed, one should be able to answer some of the following questions. For instance, if you have 1 gram of selenium-72 initially, how much remains after 12 days? Well, the half-life is 8.5 days. The decay constant is log 2 divided by 8.5 days. The number initial times e to the minus lambda t. Well, this is nominally for atoms, but atoms, grams, they're completely linear relationship. So 1 gram times e to the minus lambda times t, 12 days, you get 0.376 grams. So if you started with 10,000 atoms of selenium-72, how many atoms would remain after 12 days? Well, after 12 days, it's 0.736, so 37.6% remain. So if I started out with 10,000 atoms, I'd have 3,760 atoms after 12 days. So these relationships are the same: mass, number of atoms, they're correlated.
Other examples of equations and reactions and decays you should be able to understand from this first lecture are shown here. So for instance, if you're given a certain isotope, arsenic-66, figure out how much of that isotope remains after a given time, half a second. So how would one do that? If just a percentage, well, use the equation where I put in n naught, that's my initial amount. N at time t is this n value here. I know that I want to figure out what that percentage is, or that ratio at the given conditions shown here. So half a second, get my decay constant. The half-life of this isotope is 95.6 milliseconds. Convert that to seconds. My decay constant is 7.25 inverse seconds. E to the minus 7.25 times half a second is equal to 0.0226. A percentage is 2.66, and that's equal 2.66 is equal to that ratio. That's after a little over 5 half-lives. So that shows that if you wait a number of half-lives, the radiation decays away effectively. And nominally, as a rule of thumb, you use between 7 and 10 half-lives before an isotope fundamentally disappears. As an example of that equation, how long would it take for 90% of a given isotope, in this case zinc-65, to decay? Well, let's use this equation again. However, we need to set up so that if we're talking about 90% of it decaying, the amount that remains is 10%. So you take 100 minus the percentage that you're interested in, and that will give you this ratio value, which I show is here. The half-life is 244 days. Let's just use the value in days. Log 2 divided by that, 244, shown here. I set up my equation, solve for t. T equals 810 days. So you can use this to estimate the time or calculate the time to get any sort of ratios, or calculate the ratios at any given time.
For the boundary of the course, we're really going to go up to the forces in nature. In nature, there are 4 fundamental forces: gravity, electromagnetic, which you likely have seen before, then weak interaction, and then strong interaction. Weak interaction is used in beta decay, where neutrino interaction produces beta decay. And then strong interactions are nuclear properties, forces that hold the nucleus together. And we're going to explore and discuss nuclear properties and beta decay in terms of these fundamental interactions. So with these fundamental particles in nature, there are interactions, symmetries, and properties of particles that are consistent, that are used within nuclear physics and derived from some of the early work and continue to be utilized today. So particles can be classified as fermions or bosons. So fermions obey the Pauli principle. They're antisymmetric wave functions. They're half-integer spins. Particles that are fermions include neutrons, protons, electrons, all half-integer. Bosons do not obey the Pauli principle. They have symmetric wave functions and integer spins. So for instance, photons. We're going to utilize some of these properties in discussing transitions. As you can imagine, neutrons, protons, electrons, they're all involved in decays, and photons are involved in gamma decay. The standard model is shown here, where you've got a nucleus, as we described, quarks, that 3 quarks make up a nucleon. So a proton, shown here, 2 up and a down quark, a neutron, 2 down and an up quark, an electron much further out. Information on the quarks are shown here. Leptons include electrons and neutrinos, different flavors of electrons and neutrinos, including the electron neutrino, the muon and the muon neutrino, the tau and the tau neutrino. Bosons are force carriers, so photons, W and Z bosons, gluons, they have integer spins. As an example from this, what are the quarks in a proton and a neutron? As shown here, there's 2 up, 1 down quark in a proton. So the up has a charge of 2/3. The down has a charge of -1/3. And if I had something that had 2 ups and a down, I'd have a charge of 1. If it was neutral, well, I would have 2 downs and an up. And imagine that through beta decay, where a neutron gets converted into a proton, at the subatomic level, you have transition. So a neutron, an up and 2 down quarks, converts to a proton. One of these down quarks gets converted into an up quark. Okay, so in both lectures, a review of the topics presented here includes a history of nuclear physics research and radiochemistry, how it grew, and how the properties of the nucleus were evaluated and discovered. We'll go into that in the course and show how the nuclear data was used to understand the properties of the nucleus. We talked about discovery methods of radioelements, the methods and techniques. One of the techniques was you use some of the elements you produced earlier to make new elements. Types of radioactive decay, alpha, beta, gamma, spontaneous fission, electron capture. We also discussed the difference between gamma rays and X-rays. We gave some examples of how to utilize the data presented in the chart of the nuclides and table of the isotope. We talked and demonstrated some of the fundamental decay equations. If I know the half-life of something, I know the initial amount. At a given time, I can predict how much is remaining. And we identified some common fission products. We did that through understanding the double-humped fission curve, plus looking at the chart of the nuclides, understanding which isotopes would be produced in fission. Okay, some examples of questions that you should be able to answer include what's the outcomes of the courses, and the course outcomes are listed here. Include fundamentals of nuclear structure, chemistry of the radioelements, modern topics in radiochemistry. Discuss the discovery of radioactivity. Becquerel and the Curies used this uranium salt exposed to the sunlight. And how about the first man-made reactor, 1942, the Chicago pile. I'm from Chicago, from the South Side, University of Chicago, same area. It was a graphite moderate natural uranium reactor. We'll describe how the moderators, either water, deuterium, or graphite, influence the behavior of neutrons in a reactor.
Other questions you should be able to answer include, what are the radioelements? As is shown here on the periodic table, all elements with a Z greater than 83 are radioactive, hence they're only available as radioactive isotopes. And there are 2 elements with Z less than 83, technetium, and promethium, which are also only radioelements. You should also be familiar with the different types of radioactive decay. These include alpha decay, beta minus decay, gamma decay, positron emission, electron capture, and spontaneous fission. At this point, you should really know what these types of decays are in a very general sense. Subsequent lectures will describe these decay routes in much more detail. And finally, you should have an idea of what are suitable references for information on the isotopes. Good references that we've discussed in this lecture include the chart of the nuclides, which shows information on each isotope, and the table of the isotopes, which provides detailed information including nuclear structure and information related to radioactive decay. I hope you enjoyed Lecture 1 as the first lecture for this quarter. When you have completed Lecture 1, please comment on the blog and respond to the Lecture 1 quiz. The information in this lecture was primarily introductory in nature. The data, chart of the nuclides, table of the isotopes, and other information will be explored in more detail in subsequent lectures. There were some calculations that were described, and you should be responsible for some very basic calculations, such as decay constants, which are just log 2 divided by the half-life. The information that you should be expected to comprehend from this lecture includes the types of radioactive decay, the difference between an X-ray and a gamma ray, and you should be able to identify some basic data from the chart of the nuclides. This includes decay mode and progeny, spin and parity of isotopes, and an isotope half-life or the stable abundance of that isotope. You should also be familiar with the history of nuclear physics research that resulted in radiochemistry.